Okay, we have a short lesson on antimatter, and it kind of sounds like a strange scientific sci-fi movie kind of word, but it's actually a real thing. And in 1928, Paul Dirac was using other people's works and Einstein's ideas, and he came up with an odd formula that sort of sounded weird, but his idea was that if an electron exists, then there should also be a positive particle with the exact same mass. And later on in 1932, we saw a cloud chamber picture like we saw in the last lesson that looked like two exact same things, but one went in the opposite direction, which would mean that it would be an opposite charge. So Anderson verified that this is indeed true using the radius and charge to mass ratios of the electron, and saw that it would be the same thing if it was the exact same item except a positive particle, and that was the first antimatter particle discovered. We tend to call it a positron because it's a positive electron, but we could also call it an anti-electron. So basically up till now we've only said there's ever been three particles, electron, proton, and neutron, but now with this existence of antimatter we actually have three more. We actually have the anti-electron or positron, we have a proton and antiproton, and we also have a neutron. So the antimatter or the antiparticle would be an antineutron. So it kind of sounds weird that it's neutral, the opposite would be the opposite, but they both end up being the same mass, the same charge, but they're created in a different process. That's why we identify them as being something different. So in terms of labeling them, if it was an electron, we usually use E minus. If it's a positron, we'd say E plus. A proton, we typically write it as plus. An antiproton would be P negative. And if it's a neutron, because it's zero, we usually just say neutron, and then antineutron, we just put a little line over top. A couple of key things that happen with antimatter and their particles is we get, if you collide an electron and a positron together, because they're the exact same mass, exact same energy, just opposite charges, what happens is that we get a process that we call total annihilation. So what that means is both particles basically destroy each other and their entire mass gets converted into energy. And that energy then gets released as an EMR radiation. So this first example, it says particle and antiparticle annihilation happens in stars. One such reaction is when an electron and a positron collide and they produce two identical gamma photons. So the question's asking what is the energy of one of these photons. So basically we have the electron and positron colliding, so the charge is good, right? We have a positive and negative, so conservation of charge still occurs, but our energy then we could calculate it by just using E equals mc squared. So if we took the mass of a electron or positron, they're both the same, and times it by the speed of light squared, we can actually calculate what the energy of that particle is once it converts it into an EMR radiation. So if we take 9.11 to negative 31 times it by 3 to the 8th squared, we get an answer of 8.2 to the negative 14. So 8.2 to the negative 14 joules is the energy of the photon, and if we wanted electron volts, we could divide that by the charge of an electron, and that would give us 5.12 times 10 to the 5 electron volts, or we could say it's 512 kilo electron volts, or even 0.5 mega electron volts, however we want to do it. So the idea is pretty simple. Two of these particles are opposites. If they hit together, they're going to totally annihilate each other and just turn that mass into energy. Modern medicine has actually used some of this to our advantage. A PET scanner basically is a positron emission tomography. So what it does is they inject an isotope like fluorine-18 into a person's body. As it moves through your body, it emits positron through collisions with electrons and beta positive decay. And we think, okay, well, beta positive is bad because it's going to give off gamma radiation, but we can see the energy levels are pretty low, so it's not a huge health risk. But the idea is, as these rays are leaving the body, they have detectors that spin around the person, and they can actually map out a 3D picture of what's going on inside. So something like a knee or whatever, they can get a pretty good diagram. And with modern changes now, some hospitals are replacing PET scanners with a CT scanner, which is just basically a computer-generated type scanner too. So between the combinations, we get a pretty good way to get a digital image of the internal organs or bone structures or whatever of people that have been injured or having medical issues. So it's kind of a cool idea that you can actually take some of this physics and apply it to medicine for something good. And that's all for this lesson.